Welcome to the Chapter 14 review questions from Burian Builders, Discovering Design with Physics. As usual, we're going to skip these first definition problems and just take note of the fact that we have this constant here that we'll be using later. For question number 2, a particle with a charge of negative 7.2 millicoulombs is placed in an electric field. If its potential energy is negative 5,600 joules, what is the electric potential at that point in the field? So for this chapter, I'm going to go back to doing something that I was doing much more in earlier chapters. I got out of it a little bit for some of the chapters because there wasn't quite as much information in a lot of the problems and I didn't feel it was as necessary. But for this one, I am going to first just write out all the information and assign it the variable abbreviations like we did earlier in the year. Okay, so we have a particle with a charge of negative 7.2 millicoulombs. And so our abbreviation for that is a lowercase q, a particle charge, okay? And it's negative 7.2 millicoulombs. We know that we're definitely going to have to change the units for this and convert that to coulombs. So let's go ahead and do that first. So one of the things that I'm going to do also differently in this chapter, there are a lot of really tiny numbers. And normally and I'm sure it's the same for many of you, working with exponents is kind of a pain in the, particularly inputting it into your calculator. It's just very cumbersome, right? But we are going to use a lot of exponents in this chapter, and we're going to go ahead and use that to our advantage, okay? So when I convert this, I'm going to use an exponent. Instead of moving decimal places over and potentially making a mistake trying to get that decimal point in the right spot every time, which is a simple, easy mistake to make, I'm just going to use an exponent. And so for millicoulombs, that is going to be 10 to the negative third coulombs, right? So I'm just going to change this to negative 7.2 times 10 to the negative third coulombs, okay? Our potential energy is negative 5,600 joules. So we have, for that, PE equals negative 5,600 joules. And then we need to know what is the electric potential at that point in the field. So I'm going to do something also here. I'm going to go ahead and convert this to a scientific notation, and you'll see why I'm doing this when we get more into this chapter. But so negative 5,600 joules is going to be 5.6 times 10 to the third power joules. Okay, so for this problem, we're going to be using equation 4.1 that deals with potential energy, and that is PE equals Q times V. And of course, that's a capital V. And of course, we are trying to get the electric potential here, which is going to be in volts. Okay, that is this V, the electric potential. So let's isolate that. We have V equals PE divided by Q. And now let's plug that in. So we have negative 5.6 times 10 to the third joules. We have negative 7.2 times 10 to the negative third coulombs. Now, how putting the scientific notation in is going to help me is that I'm not going to put so much crazy stuff into my calculator, okay? I'm just going to calculate what this is and separately. So 10 to the negative third divided by 10 to the third divided by 10 to the negative third, that's going to give us 10 to the 6th on top, okay? And so in my calculator then, I'm just going to put in negative 5.6 divided by negative 7.2. And I'm not going to worry about all of the exponent part until the end, okay? And so when I do that, I'm going to get, you're going to get like 0.78 on your calculator, rounding to the two significant figures. And then you multiply that times 10 to the 6th. And so you could say 7.8 times 10 to the 5th, or we could say 780,000. And joules per coulomb, of course, is volts. Now, in the book, Dr. Wile doesn't use this abbreviation for volts, V, but that is the SI abbreviation for volts. So, in my opinion, you are welcome to use that, even though in the book he spells it out every single time. But V is the common abbreviation, and it is the standard abbreviation for volts. So, our final answer here is that the electric potential is 780,000 volts. For question 3, in the problem on the previous page, the particle was placed 45.0 centimeters away from the stationary particle that is generating the electric field. What is the charge of that stationary particle, including its sign? Okay, so we have all the information that we were given before and that we calculated from question 2. And let's see what we're given in question 3. We're given particle was placed 45 centimeters away from the stationary particle. So that is a radius. So this is going to be our R equals 45.0 centimeters. And I'm going to go ahead and keep doing this the whole way through today, just putting things in scientific notation. Now, when I'm just in the midst of calculating things, your scientific notation doesn't have to be correct scientific notation. And so rather than, again, potentially input an error or, make some kind of silly small mistake when I'm moving decimal places, I'm just going to say 45 times 10 to the negative 2 meters. And actually that should be a 45.0, right? Because we have 45.0 there. Okay. So we have radius, we have our initial particle charge, we have our potential energy, and we have the electric potential. And so with that, and we need to know what is the charge of that stationary particle, which is Q, right? That's what we need. And so for this, we can use the equation 14.2, which is that the electric potential equals K, our Coulomb's constant, times Q divided by our radius. Okay, so uppercase Q is our stationary charge, lowercase q is our particle that can move. So we are solving for this Q. So let's go ahead and rewrite that. So we have Q equals velocity times radius divided by our Coulomb's constant. So let's go ahead and plug everything in. So we're going to take our velocity from our previous problem, or not velocity, I'm sorry, our voltage, our electric potential from the previous problem, 780,000 volts. Scientific notation, right? So 7.8 times 10 to the 5th volts times our radius, 45.0 times 10 to the negative 2 meters, and dividing that by Coulomb's constant, which is 8.99 times 10 to the 9th newtons times meters squared divided by coulombs squared. Now we are getting a charge here, so our final result should just be in coulombs. So let's make sure that we have that. Okay, so remember, volts can be alternately expressed as joules per coulomb. Okay, and so that gets us rid of one of these coulombs in the coulomb squared. Okay, we can get rid of one of these meters here, and then newtons times meters is the same thing as joules. So get rid of those together. And so all we're left with is coulombs, which we're dividing it, and it's in the denominator, so it'll be at the top. So now, let's look at these exponents first. We have a 10 to the 5th and a 10 to the negative 2nd. And so that makes this 5 a 3. Then we have 10 to the 3rd and 10 to the 9th at the bottom. And so that makes up top, it's going to be a negative 6, right? Because we subtract what's at the bottom. Okay, so whatever we get when we multiply these numbers here without their exponent, the scientific notation exponents, then we're going to multiply that times 10 to the negative 6. So when we multiply out 7.8 times 45.0 times 8.99, getting that to two significant figures, we're going to get 39. And so that's 39 times 10 to the negative 6, or 3.9 times 10 to the negative 5th, and we're in coulombs. Okay, alternately, you can rewrite that as 0.0000039 coulombs. Either answer would be correct. Okay, so our final answer here is that the charge is 3.9 times 10 to the negative 5th coulombs. Question 4, a particle with a mass of 1.1 grams, a charge of 3.2 microcoulombs is placed 22.5 centimeters away from a stationary charge that is 12.1 microcoulombs. If the particle starts at rest, how fast is it traveling when it is 35 centimeters away from the stationary charge? So there's a lot of information we're given in this, and this is really the reason why in this chapter I just want to break down everything that I've been given and put it into its variable with the abbreviation, so I can easily just set it up into my equations. So let's get going on that. So we have a mass, and that is 1.1 grams, and we need to convert that into kilograms. And so we're just going to put that in scientific notation. 1.1 times 10 to the negative 3 kilograms. Okay, we have a charge that is a particle charge, so it's a lowercase q, and that is 3.2 microcoulombs. And the nice thing about this is it's so much easier to write this in scientific notation than write 0.000032. So it's going to do that. 3.2 times 10 to the negative 6 coulombs. Okay, it's placed 22.5 centimeters away, so that is a radius, and we're given two different radii. So we're going to label them 1 and 2. Radius 1 is 22.5 centimeters. And let's just put that into scientific notation as well as we convert that into meters. And like I said before, I'm just going to use incorrect scientific notation just to write it out for these problems and give myself as few opportunities to make mistakes as I can. So 22.5 times 10 to the negative 2 meters. Okay, let's go ahead and get the second radius here. So the second radius that we're trying to determine something about is that when it's 35 centimeters away, so we're just going to do the same thing, 35.0 times 10 to the negative 2 meters. Now we were given the charge of the stationary charge. That's 12.1 microcoulomb. So when it's stationary, that's the uppercase Q. And I have 12.1. Again, I'm just leaving it as 12.1. So that equals 12.1 times 10 to the negative 6 coulombs. And then we're given that it started at rest. So we have an initial velocity, which I'm going to call V1, even though we usually say V0. If you wanted to, you could call this all like R0, RF to go with the other notations that we've used with initial and final. So V1 equals 0, and V2 is what we were trying to determine. Okay, so the key to this problem is that knowing what we know about potential energy and kinetic energy. Okay, so when there's zero velocity, kinetic energy equals 0 because our kinetic energy equation includes velocity in it. So that means all of the energy, the total energy, equals the potential energy. Now in the second velocity, there is some velocity that's we're going to determine, and so therefore there is some kinetic energy, and the total energy is going to be a combination of potential energy plus kinetic energy. There's still going to be some potential energy that hasn't been used, and as well as the kinetic energy at that point in time. And so what we can use then is the change in potential energy, because however much this potential energy at the zero velocity changed from this first radius to the second radius, that is how much the kinetic energy changed in reverse. So if we lose potential energy, for example, we're going to gain kinetic energy, right? And that's the only way we can do this here, right? Because all the energy is potential energy. We're going to lose it and then gain kinetic energy. And then once we have the kinetic energy, we can use that and the mass to determine our velocity at the end. So let's get started on that. So our initial goal is going to be to determine what our change in potential energy. And so that's using equation 14.3, which we haven't used yet in this set of review problems, which is the change in potential energy equals our charge on our particle times our change in electric potential. Now, we weren't given a change in electric potential, but we have everything that we need to determine that. We're just going to use the same equation that we used up here in problem 3, equation 14.2, where the electric potential equals our Coulomb's constant times our stationary charge divided by the radius. And we'll do that for both radii and then determine what the difference in the electric potentials are. So for the first one, we're going to call it V1, just because I'm labeling everything 1, 2. If you're labeling it 0F, then you call it that. Equals our Coulomb's constant, 8.99 times 10 to the 9th newtons times meters squared divided by Coulomb squared. Multiplying that times our stationary charge, 12.1 times 10 to the negative 6 coulombs, and dividing it by our first radius, 22.5 times 10 to the negative 2 meters. Now we are getting voltage, which is joules per coulomb. So let's first make sure that units wise we're going to get there. Our meters here will cancel. once. 1 coulombs will cancel, and we get newtons times meters, which is the same as joules, over coulombs, which is voltage. So first thing I'm going to do is just cancel out my 10's exponents to see what I'm going to end up with. So 10 to the 9th, 10 to the negative 6, we'll end up with 10 to the 3rd up top. And then when we have 10 to the 3rd and 10 to the negative 2nd below that, we're going to add that 2 up here. And so we'll actually end up with 10 to the 5th. So we can multiply all of these individual parts, 8.99, 12.1, 22.5, and then multiply all of that times 10 to the 5th to get what that first electric potential is going to be. So when we do that, we are going to get 4.83, rounding to 3 significant figures there. And luckily for us, it's already in a nice scientific notation format, which is the decimal after 1 place. And so we can just tack on a 10 to the 5th at the end of that. And that is going to be, we're going to go ahead and keep it in joules per coulomb. Alternately, you could write that as 483,000. Okay. You could also write this in volts if you wanted to change it to volts, but we'll probably be changing it back later. So, okay. So now we'll get our second voltage or electric potential. And it's writing out the same numbers except for that radius at the bottom. So Newton times meter squared over coulomb squared times 12.1 times 10 to the negative 6 coulombs. And this time we're dividing it by 35.0 times 10 to the negative 2 meters. Okay. All right, we don't need to worry about making sure our units will work because we've already essentially done that. We've also already essentially figured out what our scientific notation exponents is going to be. So we can just go ahead and say this is 10 to the 5th and not worry about calculating it out because we had the same exponent there as before. So when we now multiply 8.99 times 12.1 divided by 35, we will get 3.11. It's so nice how it gave us an easy one that we didn't even have to change anything to keep it in proper scientific notation. We just tack on that 10 to the 5th at the end. So now we have our first and second voltage, and we can determine our change in voltage or electric potential. Remember, when we determine a change, it's always the end change minus, or the end value minus the beginning value. So it's going to be 3.11 times 10 to the 5th joules per coulomb minus 4.83 times 10 to the 5th joules per coulomb. And we will get a negative 1.72 times 10 to the 5th joules per coulomb. Okay. So now we have our change in electric potential, and we can insert into this equation to determine the potential energy. So we have our particle charge, 3.2 times 10 to the negative 6 coulombs, times our change in electric potential, negative 1.72 times 10 to the 5th joules per coulomb. And here you can see why I left it in joules per coulomb instead of saying volts, because the coulombs are going to cancel, and I'm going to be left with joules, which is our energy unit. So when I look at the exponents here, this is going to be negative 1 when you multiply that times 10 to the 5th, okay? So what I get here when I multiply 3.2 times negative 1.72 is a negative 5.5, and so then since it's times 10 to the negative 1, we're going to just move that decimal place over 1 and look at 0.55, of course, negative joules. So that is our change in potential energy. So it means that from our first spot to our second spot, our first radius to our second radius, the potential energy decreased by negative 0.55 joules. Now there's still some potential energy there, but whatever it decreased by, that means it was replaced by kinetic energy. And so our kinetic energy then equals a positive 0.55 joules, okay? It decreased in potential energy, but whatever it lost in potential energy, it had to go into something, it had to go somewhere, and it went into the kinetic energy, so it's positive there. So now that we have the kinetic energy, we can use our kinetic energy equation from way back when. Kinetic energy equals 1/2 mass times velocity squared. And we're determining the velocity, so solving for velocity. Velocity equals, we're going to have 2 times the kinetic energy divided by our mass, and of course we're taking the square root of that. So now let's plug that in. We have 2 times 0.55 joules, dividing that by our mass, 1.1 times 10 to the negative 3 kilograms. I'll be taking the square root of that. Now this is one where it actually might have been simpler to, instead of making this an exponent, go ahead and write it out. So 0.0011 kilograms for the sake of putting this in the calculator. And we get, when we round to two significant figures, 32. And let's look at the units real quick. Okay, so joules is newtons times meters, right? And that's not helpful because we're dividing by kilograms. So let's break that down. Kilograms times meters, that's per second squared, that's newtons, times meters, okay? So that's what joules is converted to. And so we cancel out the kilograms, we're left with meters times meters divided by seconds squared. And so when we take the square root of that, we'll get meters per second. So we're finally at our answer. The velocity at 35.0 centimeters is 32 meters per second. For question 5, we have a particle that is 9.5 kilograms with a charge of negative 4.1 millicoulombs shot towards a stationary negative 8.2 millicoulomb charge with a speed of 714 meters per second. If it begins 35 centimeters from the charge, how far will it be from the stationary charge when it stops? So let's break this down. We have a mass, and we're already given the mass in kilograms, so yay, no conversions on this one. Okay, we have our particle charge, lowercase q, negative 4.1 millicoulombs. So let's convert that to coulombs. Negative 4.1 times 10 to the negative 3 coulombs. You can read that. Okay, we have a stationary charge that is negative 8.2 millicoulombs, or negative 8.2 times 10 to the negative 3 coulombs. We have a initial speed, our velocity 1 equals 714 meters per second. And our radius 1 is 35.0 meters per second. Then our velocity 2 is it has stopped. I would need to know what the second radius is. So in this one, we're given the initial velocity and the final velocity, and we just don't have the radius. But because we have both velocities, we can figure out what the kinetic energy is based on the first velocity, and therefore what the change in potential energy is, because the second velocity has a kinetic energy of 0, right? And so same as the last question, just in reverse, whatever that kinetic energy is, the potential energy is going to be the same but opposite. So let's determine that kinetic energy. We have Ke equals 1/2 mass times velocity squared. Our mass is 9.5 kilograms times 714 meters per second squared. And I'm going to put this answer in scientific notation because it is a big number. I have two significant figures, so 2.4 times 10 to the 6 joules, right? Then we have kilograms times meters per second squared times meters is how we get that joules. Okay, so this is our kinetic energy, and then it is positive. So at the end, though, our kinetic energy is 0. So it actually lost 2.4 times 10 to the 6 joules in energy, in kinetic energy, and therefore gained 2.46 times 10 to the 6 joules in potential energy at the end. Okay, so with our equation, our change in potential energy equals Q times delta V. Our potential energy is going to be 2.4 times 10 to the 6 joules. Okay, so even though it's positive here, this is just a calculation of what the kinetic energy was at this point, but it had to have lost that energy, okay, and therefore potential energy is gained. I'm going to make sure that you understand that. So we have potential energy, we have our particle charge, and we can determine what our change in electric potential is. So let's do that, solving for the electric potential. It's going to be delta V equals delta PE divided by Q. .4 times 10 to the 6 joules divided by negative 4.1 times 10 to the negative 3 coulombs. Okay, so we have 10 to the 6 and 10 to divided by 10 to the negative 3. So it's going to be the same as 10 to the 9th up top. And so we have 2.4 divided by negative 4.1, and we're going to get negative 0.59. And I'm going to move that decimal place over 1 to make it 5.9. And so with 0.59 times 10 to the 9th, but I moved it 1 over, and so it's going to be 5.9 times 10 to the 8th joules per coulomb. That is our change in voltage. Now to get the radius of the second one, we need to determine what each of the electric potentials are and then solve for radius. So our change in electric potential is obviously going to be our V2 minus our V1, right? And so we need to be able to determine what the V2 is. And so to do that, we're going to solve for V1, or figure out what V1 is first. So we can do that with our equation of V equals K times Q divided by R. So let's determine our first electric potential. 8.99 times 10 to the 9th newtons times meters squared times coulombs squared times our stationary charge, negative 8.2 times 10 to the negative 3 coulombs, divided by our first radius, 35.0 times 10 to the negative 2 meters. So let's check our units. I have a meters. 1 meters cancels, 1 coulombs canceled, joules per coulomb. Let's look at our tens exponents. So 10 to the 9th minus 3, we have 10 to the 6th plus 2. So whatever we get, we'll multiply it times 10 to the 8th. So we have 8.99 times negative 8.2 divided by 35, and that gives us a negative 2.1 with two significant figures. And so we just multiply that times 10 to the 8th, and we're in joules per coulomb. Okay, so now we have our delta V, we have our V1, and we can solve for V2. So our delta V, negative 5.9 times 10 to the 8th joules per coulomb. We're going to add the V1 to get V2, so plus a negative 2.1 times 10 to the 8th joules per coulomb. And we're going to get a negative 8.0 times till 10 to the 8th joules per coulomb, or our voltage. We can just leave this in joules per coulomb. We're still not done, right? We need to figure out the radius, but now we can use this equation to solve for R. So our R is going to equal K times Q divided by V. So 8.99 times 10 to the 9th newtons times meters squared per coulomb squared times our Q, negative 8.2 times 10 to the negative 3 coulombs divided by our electric potential, negative 8.0 times 10 to the 8th joules per coulomb. Okay, so let's make sure we end up with meters because we are trying to get a radius. All right, we have coulombs, and coulombs cancels with those coulombs. We have newtons times meters, which is the same as joules. So we take off one of the meters and the newtons and the joules, and that cancels. And so we are, in fact, left with meters. Now let's look at our scientific notation exponents. So 10 to the 9th and 10 to the negative 3, we get 10 to the 6th and minus 8. So we're going to end up with 10 to the negative 2, what we multiply our answer by. And so we're going to get 9.2 times 10 to the negative 2 meters, right? Or of course you could write it out and say 0.092 meters as your answer. Either form would be correct, or you could say 92 centimeters. So we are finally done. So our final answer is that the particle stops 0.092 meters away from the stationary charge. For question 6, a charged particle travels from the positive side of a 9-volt battery to the negative side. If it gains potential energy as a result, what is the sign of the particle's charge? Okay, so since it went from the positive side to the negative side, the electric potential went from a positive value to a negative value. So that means that the electric potential decreased. So our delta V, our change in electric potential, is negative. However, the change in potential energy equals Q, our charge, times delta V. So if the change in potential energy is positive, because it did gain potential energy, that means that the Q must be negative, okay? So we, from going to positive to negative, okay, and this means that our delta V equals negative, okay? But the potential energy is positive. So PE equals positive. And so if we look at our equation, PE equals Q times our change in electric potential, then this means that we have a plus equals what? Times a negative, okay? And so therefore, this Q value, this particle charge, has to be negative. For question 7, right before a lightning bolt strikes, what would be the sign of the electric potential, the change in electric potential, or delta V, for anything that travels from the ground to the bottom of a cloud? So if you remember from the discussion about lightning strikes, the bottom of the cloud has negative charges. And so negative charges make a negative potential. The ground has positive charges. So we have cloud is negative and the ground is positive. Okay. So moving from positive to negative means that the electric potential decreased, and so that means the delta V is negative. For question 8, what kind of charging happens to make lightning? What is the stepped leader? What about the return stroke? And how does the energy of the stepped leader compare to the return stroke? For question 8, what kind of charging happens to make lightning? What is the step leader? What about the return stroke? And how does the energy of the step leader compare to the return stroke? So most of this question is spelled out pretty clearly in the big discussion on lightning that starts on page 381 and goes through page 383. The exception to that might be the first part of this question, the what kind of charging happens to make lightning. And just remember that there's friction that is causing that charge to develop. So that's one hint, but if you really can't remember, in comprehension check question 6, it asks the exact same question. And of course, the explanation for that is in the book. So I'd just refer you to that. For question 9, what two types of capacitors were discussed in this chapter? I'm going to again refer you back to the reading on this one. Page 386 talks about the two different types of capacitors that are ultimately discussed in this chapter are both on that page, and it spells that out pretty clearly, so I'm not going to give you that answer. For question 10, what can you say about the electric field found near the center of a charged parallel plate capacitor, and does that apply to the edges as well? So I'll just direct you to the drawing at the bottom of page 386. And there's discussion around that drawing. But essentially, near the center, that electric field is constant. You can see in that drawing all of those straight arrows, and that's showing constancy. But near the edges of it, it is not constant. And you can see the difference again, looking at that drawing on page 386 if you don't quite understand what this question is referring to or what I mean. Question 11. A parallel plate capacitor is made of 1.2 by 1.2 centimeter plates that are separated by a 0.2 millimeter dielectric. If its capacitance is 15.3 microfarads, what is the electric permittivity of the dielectric? So for this one, we're going to be using the equation 14.4, and that is that the capacitance equals the electric permittivity times area divided by the diameter, which is the distance between the two plates. So let's go ahead and write out the parts that we have. So our area equals 1.2 centimeters by 1.2 centimeters. Let's get that into meters. So that's going to be 1.2 times 10 to the negative 2 meters times 1.2 times 10 to the negative 2 meters. And that is going to get us 1.4 times 10 to the negative 4 square meters. Okay, we have the dielectric diameter. That is 0.20 millimeters. And convert that to meters. Again, don't worry about correct scientific notation at this point. So just put 0.20 times 10 to the negative 3 meters. And then we have the capacitance, C equals 15.3 microfarads. So let's convert that into farads. That's going to be 15.3 times 10 to the negative 6 farads. Okay, so we are solving for electric permittivity. And so that is going to be electric permittivity equals the capacitance times the diameter divided by the area. Let's plug all of that in. 15.3 times 10 to the negative 6 farads times our diameter, 0.20 times 10 to the negative 3 meters, divided by our area, 1.4 times 10 to the negative 4 square meters. Okay, so our electric permittivity should be in farads per meter. So cancel out 1 meter, and that leaves us with farads per meter. Pretty simple there. Okay, let's look at our scientific notation here. So we have 10 to the negative 6 times 10 to the negative 3. So that's going to give us 10 to the negative 9 divided by 10 to the negative 4. So negative 9 plus 4, we're going to end up 10 to the negative 5 here. So then we calculate 15.3 times 0.2 divided by 1.4. And we're going to get, with two significant figures, 2.2. And then we add or multiply this times 10 to the negative 5. Farads per meter. So the electrical permittivity is 2.2 times 10 to the negative 5th farads per meter. For question 12, the capacitor in question 11 is charged by a 6-volt battery. What is the charge stored on each plate? So for this problem, we have a capacitor, we have a voltage, which is going to be our electric potential difference in electric potential, our delta V, and we need a charge, which is our uppercase Q, right? So this is our equation 14.5, where Q equals our capacitance times our difference in electric potential. And so we have the capacitance that we were given up above, 15.3 times 10 to the negative 6 farads. We have our difference in electric potential, 6.0 volts. And then we're going to get our charge, which is coulombs. Now, farads can also be written as coulombs per volts, okay? And so that's what's going to serve us best here. So our charge equals 15.3 times 10 to the negative 6 coulombs per volt times 6.0 volts. And that is going to give us 92, and then times 10 to the 6, but we need to get this in better standard notation, 10 to the negative 6, I should say. And so we're going to change that to 9.2. And so instead of 10 to the negative 6, 10 to the negative 5. And volts canceled, so we have coulombs. The charge on each plate is 9.2 times 10 to the negative 5 coulombs. Question 13, a parallel plate capacitor uses a 0.0955 millimeter thick dielectric with a electrical permittivity of 1.56 times 10 to the negative 7th farads per meter. If each plate has an area of 0.0045 square meters, what will be its potential difference when each plate holds 15.0 microcoulombs of charge? Let's just write out what we have first here. So we have a diameter equals 0.0955 millimeters, and we need to get that in meters. Just times 10 to the negative 3 meters. Okay, we have our electrical permittivity of 1.56 times 10 to the negative 7th farads per meter. We have area 0.0045 square meters. And we have our charge is 15.0 microcoulombs. Just multiply that times 10 to the negative 6 to get coulombs. Okay. So what we need is our potential difference, so our delta V, and we're going to need to start with getting our capacitance. Okay, so we're going to use the same equation from the last problem, Q equals C times delta V, because we have Q and we have everything we need to get C in order to solve for our potential difference. So let's get our capacitance using C equals our electrical permittivity times area divided by diameter. So 1.56 times 10 to the negative 7th farads per meter times our area, 0.0045 meters squared, divided by our diameter, 0.0955 times 10 to the negative 3rd meters. So let's look at the units. Our meters are going to all cancel. We're going to be left with farads, which is our unit of capacitance. Let's look at our exponents here. We have 10 to the negative 7th and 10 to the negative 3. So this is going to end up as 10 to the negative 4th. And let's see what this calculates out as. We get 0.074, and then we're going to multiply it times 10 to the negative 4th farads. I'm going to leave this in this notation. This isn't our final answer, and so rather than change it to be correct scientific notation, I'm just going to leave it as is and bring it down. So now that we have the capacitance, we can use our equation where our charge equals our capacitance times our potential difference and solve for the potential difference. So that's going to be our delta V equals our charge divided by the capacitance. So plugging that in, we have 15.0 times 10 to the negative 6 coulombs divided by 0.074 times 10 to the negative 4th farads. So 10 to the negative 4th and 10 to the negative 6, we're going to end up with 10 to the negative 2 up top. And then when we do 15 divided by 0.074, we get 202, which we only need two significant figures here. So 200, but this is to the -2. So we're going to move our decimal place. And so we actually get 2.0 as that answer with no other scientific notation. So 2.0 coulombs per farad, which we do need to convert this since we are just solving for the potential difference to what our unit for potential difference is, which is the volt. So the potential difference is 2.0 volts. For question 14, suppose you have an object that is positively charged. If you connect it to the ground, what will happen to its charge? What is coming from the ground to make that happen? So you are connecting it to the ground, and ground is an infinite sink or source of electrons. So since this object is positive, it's going to be attracting electrons from the ground. So the charge is going to go to 0 because all of those positive charges are going to be canceled out by the charges coming up from the ground. For 15, when both sides of a capacitor are connected with a conductor, what flows through the conductor and in what direction is the flow? So electrons are what move in a conductor, and they always are going to go toward positive charges. So the electrons flow from the negative side to the positive side. For 16, when both sides of a capacitor are connected with a conductor, in what direction does conventional current flow? So this is where in the book it's talking about how they believed something for so long that they just decided to stick with that terminology even when they found out that that wasn't quite the way it worked. And so conventional current is the flow of positive charges, even though we know it's electrons that are actually moving. But that's the way we draw the current. So in conventional current, it's going to flow from the positive to the negative side. So when we draw it out, that's what is being drawn out.